Hello and welcome to another lecture of classical motion of a single particle. So, finally, we derived the Euler-Lagrange equation or the Lagrange's equation of second kind, and we have actually derived this using the D'Alembert's principle, which actually is one of the possible methods by which you can derive the Euler-Lagrange equation. And we found that if we use this method, this is very specific to classical mechanical systems, and we found that Lagrangian of a particle is actually given by T minus V. Okay. But of course, you know that whenever this definition is meaningful, but in order to make this definition meaningful, I have to assure that the particle is actually moving in a conservative force field, where you actually have a meaningful potential. Now, you can actually tell me that this is a little bit confusing, because you said that Lagrange's equations or Euler-Lagrange equation should not use any concept of force while deriving. I agree. So, what we actually will do, because we know that V is associated with conservative force fields, that is why I said that, but the proper way of putting this will be that I have to make sure, in order to have a meaningful Lagrangian, I have to make sure that the Lagrangian is associated, or the motion of the particle is associated to some scalar potential function. Okay. I am not in that way, I am not associating this to a conservative force field. Okay. Now, if Lagrangian is given as T minus V, okay, then actually you can show that finally you can derive all the equations of mechanics without any problem. For example, here for this course for a single particle, and as I just mentioned last week, that this Lagrangian can be also used for any number of particles. Okay. For a system with many particles, for a system with even where you do not have classical mechanical particles either. Okay. You can have different type of systems. For example, I said in economics, in epidemiology, in biology, you can have different type of systems where Lagrangian can be of importance. But this form, you have to then understand that this form T minus V may not be kept intact for those systems. Okay. So, this T minus V is the form of a Lagrangian for a mechanical system. Okay. For our course, this is much more even specific, even for us a single particle. Okay. Mechanical system whose motion is associated with a scalar potential V. Okay. If you remember, we also used some other things. So, first we said that the V should be existing, but V also should be a function of x, y and z, that we used for our derivation. Okay. So, now the question is, if V is a function of velocity, let us say velocity dependent potential, if we have a system like that, can we also have a meaningful Lagrangian? I will come to that point at the very end of this week's lecture. Okay. Before that, let me just tell you once again, this is the kinetic energy. So, this is the potential energy. Okay. And we just said that this is the information we know. So, someone said that this is a system whose Lagrangian, for example, is given by half m x dot square minus some V of x, for example. Okay. This is the information I start with. Now, how to find the equations of dynamics for that? I know that the Lagrange's equation is finally given by ddt of del L del Qi minus del Qi dot minus del L del Qi is equal to 0 for all I running from 1 to n, where n is the number of the generalized coordinates. So, this equation is not just the one single equation, this is true for every generalized coordinate, and that is the symmetrical, that is a symmetric victory of this formulation over normal Newtonian formulation. So, for example, if you just start writing Newton's second law, what in general you get? You get that okay, mr double dot is equal to F. Now, if you say that okay, I want to decompose the whole thing in Cartesian systems, then you have mx double dot is equal to Fx, my double dot is equal to Fy, and mz double dot is equal to Fz. Can you do the same business with r theta phi? Can you write r double dot is equal to Fr, m theta double dot is equal to F theta, and m phi double dot is equal to F phi? The answer is a big no. And you actually know that in the radial direction, actually just in 2D, the force expression is m times r double dot minus r theta dot square, and in 3D it will be actually much complicated. You can find it out okay, by yourself. So, you see that this symmetry does not get propagated to this system, this coordinate system, okay, although the particle or the system under investigation is the same. Okay. So, it is a more like it is a symmetry, coordinate system specific symmetry, and this is only possible for Cartesian system. But as I said that for many problems the symmetry, the coordinate system of symmetry is a different system than a Cartesian one. Okay. Then what to do? Of course, you can say that I should be happy with this type of forms, that is true. But here the main advantages is that, let us say if your generalized coordinates are now theta and phi, without thinking anything, just blindly and bluntly you can write ddt for that system del L del theta dot minus del L del theta will be 0, and ddt del L del phi dot minus del L del phi will be 0, given you have correctly found the Lagrangian. Okay. So, this is a very important step forward for us for having a symmetric analytical formulation of mechanics. Okay. So, now coming back to this point that if my L is given like this, what I have to do? So, I can write, so once again L is half m x dot square minus v of x. Okay. So, this is a scalar function of x only. Then del L del x dot will simply be equal to m x dot, and del L del x will be equal to minus del v del x. Now, if you just write this equation ddt del L del x dot minus del L del x will be 0, then this actually gives us m x dot ddt will be equal to del L del x, which is minus del v del x, and this is m x double dot is equal to minus del v del x, and this is nothing but your famous Newton's second law for a particle moving in a conservative field. I am just saying that according to your knowledge, this is the Newton's second law for a particle moving in a conservative field having potential V. Okay. So, this is the power of this formulation, that finally you are actually finding this equation of motion. Sometimes, now here there is a point that you can actually think that maybe for every, maybe corresponding to every generalized coordinate, I will actually have a new or a separate equation of motion. Sometimes this is not also the point, okay, that, and because you think that because in your mind setting this is somehow implanted that an equation of motion is always F is equal to m a. Okay. In this framework we can also generalize the situation, and actually an equation of motion is any correct equation of motion, any necessary information regarding the motion. I am coming to that point now. So, let us say I am saying a particle is moving, along some trajectory in 2D plane. Okay. I do not know what is the nature of the force, but the potential and the potential associated is a function of r only. Okay. So, right from the beginning I said that for the particle the potential energy will be equal to some V of r, and what will be the kinetic energy? This is 2D. So, I right from the beginning I choose my coordinate system of convenience, that is half, that is the plane polar coordinate system, where kinetic energy is half m r dot square plus r square theta dot square. You know this, okay. And if you write this thing now, then your Lagrangian will be, so this is your T, this is your V, Lagrangian will be half m r dot square plus r square theta dot square minus V of r, and your Euler-Lagrange equation will simply be given by d dt. So, how many equations do you have? We have two Euler-Lagrange equations, one related to r, another related to theta. So, the first one will be d dt del L del r dot minus del L del r is equal to 0, and d dt del L del theta dot minus del L del theta will be equal to 0. Okay. I can directly find from this equation, I just change the color, what is del L del r dot? That is again m r dot. Okay. What is del L del r? Once again that is, so del L del r is nothing but minus del V del r. Okay. But is this all? No. Now you say we are overlooking something, this, okay, and this one is actually will give you a non-zero contribution for del L del r, which is minus, so you will have m r square, so theta dot square, sorry. So, this will be del L del r, so del V del r plus, so that will be half m theta dot square times 2r, so which will be 2r, yeah. So, it will be minus del V del r plus m r theta dot square. Okay. You combine this two, okay. What you will have? So, you should finally you should have this equation. So, d dt of m r dot will be equal to del L del R, which is minus del V del R plus m r theta dot square, and this is nothing but m r double dot. So, I can take this to this side and you will have m r double dot minus r theta dot square is equal to minus del V del R. So, you see here the biggest thing is that you are actually recovering the same thing as you recover in the case of Newton's law. Okay. But now you are coming from a form where you do not have to think that you are writing for r or theta. The form is so symmetric. Okay. What happens for theta? So, before just okay, I can actually do here. Yeah. So, what happens for theta? I can take del L del theta dot to be equal to m r square theta dot. Okay. And what is del L del theta? You see, surprisingly, although r and r dot both are present in the expression of Lagrangian, theta dot is present, but theta is not present. So, that is why del L del theta is 0, and I have finally m r square theta dot will be equal to so I just write the properly, so that this is the first time you are doing. So, it is good. So, Euler Lagrange equation actually implies ddt of m r square theta dot will be equal to 0. So, m r square theta dot is equal to constant. Okay. You can call that L. Okay. So, you see that this is a point where you may stuck a little bit. Tell me honestly, what did you think? You thought just like you found this equation for r, you could actually found the other equation along the theta cap direction for Newton's second law if I do this thing. Okay. Euler Lagrange equation with respect to theta, but that you are not finding. Okay. But you are what you are finding is actually something is also true, you know, for a 2D motion, that is the angular momentum vector has a constant magnitude here. Okay. And that we have used actually for such type of motions, and one such. So, which is this motion finally? If you remember, this is a possible Lagrangian for a particle which is moving under a central force, and for that the angular momentum is a constant vector. So, just like the direction, its magnitude is also conserved, and here this equation is actually is not giving a f is equal to ma, but this is just giving that something is conserved. Okay. So, also at this point it is a very good thing to learn that whenever we say that whenever you put the Lagrangian in the Euler Lagrange equation for a system, the outcome is not always an equation of dynamics in Newton's sense. This is some information. Now, I have a question for you. You please think, otherwise I will tell you. Okay, I will tell you in the next lecture. So, this is that how actually finally you have to find, how you can find in this framework the force equation in the theta cap direction. Of course, you thought that could be done by using the Euler Lagrange equation with respect to theta, but that did not work. Okay. So, what is the trick then? I am just going a little bit with some other interesting things about this Euler Lagrange equation. So, you see that the first thing, so mainly in this lecture I will try to describe some properties of Euler Lagrange equation. Okay. So, I will continue of course in the next lectures as well this. So, the first important property is that ddt of del L del Q I dot minus del L del Qi is equal to 0, okay, where Qi is a generalized coordinate, and this is true for all generalized coordinates equally. Okay. Now, the first point is, if L does not explicitly contain any Qi, okay, let us say some Qi star, okay, a specific Qi, okay, it can be more than one or more than one, or okay, specific Qi or a more than one specific Qi's. So, for example, let us say out of 3 Qi's in a system, 2 have this properties, okay, that 2 are absent from the expression of Lagrangian, but their dots exist in the form of the Lagrangian. For example, this thing, half m r square minus r dot square plus r square theta dot square minus v of r. You see that this does not contain theta, but contains theta dot. Okay. This type of coordinate is known as cyclic coordinate. If a coordinate, if a generalized coordinate is a cyclic coordinate for a system, okay, then what happens, that the corresponding, if for example Qi star is absent or it is a cyclic coordinate, then del L del Qi star is 0 from this one, okay. And if this is 0, then I can actually say d dt of del L del Qi star dot is always 0 and del L del Qi dot star is conserved, okay. This quantity is known as the conjugate momentum of the coordinate Qi star. So, for any generalized coordinate Qi, for Qi, okay, conjugate momentum is given by del L del Qi dot, okay. So, if Qi or Qi star is a cyclic coordinates, its conjugate momentum is conserved, okay. So, you see in this problem theta is a cyclic coordinate. So, its conjugate momentum, since theta is an angle, and if you think that theta is a generalized coordinate, then the corresponding momentum will be angular momentum, and that is exactly what we get from this one, okay, this thing, okay. Now, you see again this d dt del L del Qi dot minus del L del Qi is equal to 0. I add to this L some arbitrary constant with the same dimension, of course. So, for example, here L, you can easily understand L has a dimension of energy because this is T minus V. So, I can now add L plus some K, which is a constant, okay, having the dimension of energy. Is it also a valid Lagrangian for the system? Yes, because if you see carefully this equation, okay, any constant, if it is added or subtracted from this original Lagrangian, actually also satisfies this Euler Lagrange equation, because Euler Lagrange equation just associates the derivatives, okay, of Lagrangian, and that is why if L is a Lagrangian, then L plus minus k is also a valid Lagrangian. Okay. And if you now take L to some beta times L, where beta is a constant, will that be also a valid Lagrangian for this system? Again, my answer will be anything which is for a given system, anything which is just satisfying the Euler-Lagrange equations, okay, they are valid Lagrangians. Okay. Now, for a given system where exactly we put this specific condition that this is for a given system in the choice of the generalized coordinates. Okay. So, if L is transformed to beta L, let us say 2L, 3L, 0.56 times L, whether this is also a valid Lagrangian? Mathematically, yes. You can say yes. If again, if you just multiply this beta throughout this equation, okay, this will not change, and that is why again you see that this is a valid Lagrangian. I mean, actually this one is a valid Lagrangian. But now the point is that whether it will simply always have the simple usual meaning of the Lagrangian, that is t minus v. If you now say t minus v times root over 3 by 2, what is the meaning of that? Of course, that is a little bit difficult, and that is why we always choose a meaningful Lagrangian. Okay? But mathematically, no one can prevent this from being a good Lagrangian. Finally, I will of course continue discussing such properties in the next lecture as well, but I am simply just doing something that we have already said that Lagrangian in general can be the property of, okay, it can be a function of the generalized coordinates, generalized velocities, and also explicitly the time. Okay. So, if I now say Lagrangian, then what is dl dt? So, dl dt is actually then del L del t plus del L del qi I would say dqi dt plus del L del qi dot dq dot qi dot dt. There is a summation over the, so just for n dimensional space, let us say small n dimensional space, for small n dimensional space which is usually 2, 3 for us space. Okay. So, n dimensional space simply means that n is the number of generalized coordinates, that is, this is the dimension of the space with effective number of degrees of freedom. Okay. So, for example, for a particle while moving on the surface of a sphere with constant radius, okay, n will be equal to 2. So, you will see that this is simply I is equal to 1 to n and I is equal to 1 to n. So, this can go up to n, where n is the actually you can say that number of generalized coordinates. Okay. If this is true, then I can actually write this is equal to del L del t plus, so summation over I1 to n. Okay. I can simply say this thing is qi dot by definition. Okay. So, I will actually say that this is qi dot, and what is this? This one is by Euler-Lagrange equation is nothing but, if you just see this equation carefully, this is nothing but ddt of del L del qi. Okay. And then plus you have summation over I 1 to n del L del q I dot oh sorry, this is del L del Qi dot, yeah. So, d dt of del L del Qi dot, and now here you will have del L del Qi dot times d dt of Qi dot. Okay. So, you can write again T, you can take the summation out I 1 to n, then d dt of Qi dot times del L del Qi dot. Okay. Now, I say that okay, I started from dl dt and I have this expression, I can actually say okay. So, this d dt and the summation can commute because they are totally independent. D dt is just the time derivative and summation is just acting on the number of generalized coordinates. So, I can actually have d dt of, I can take this thing on one side L minus summation over I 1 to n Qi dot del L del Qi dot, okay, is equal to del L del T. This is a fantastic result because if del L del T is 0, that means if the Lagrangian does not explicitly depend on time, just exactly the Lagrangians you have seen over here or here, okay, they are not depending on time, then what happens that del L del T is 0 and d dt of these will also be equal to 0, and that means L minus summation over I 1 to n Qi dot del L del Qi dot will be a constant. Now, I just use my definition that L is equal to T minus V, okay, where T is nothing but summation over I 1 to n half m Qi dot square, okay, minus V. I can write just for example, I can write just I can write this, okay. So, V is a function of Qi's. Qi means just not one I, it can be generalized, it can be depending on more than one generalized coordinates, but only coordinates, not velocities, okay. If I write this, then you see that what I will have. So, first I make this thing highlighted that this will be constant, okay, when del L del T is 0. That means your Lagrangian does not explicitly contain any time, but what will be this one, okay. Actually, then you can actually have to calculate. So, what I will do, I will not do the general calculation, but I will do just, I take a specific example, I take the example of a particle, single particle moving under some potential x y, function of x y z, okay. So, what will be Lagrangian? That will be half m x dot square plus y dot square plus z dot square minus v of x y z. I can see here, since there is no further constraint, since there is no further constraint, one actually can take x, y and z to be the system of generalized coordinate. That is also possible for this system. The Cartesian system is the system of generalized coordinates, okay, and you will have this quantity is to be determined. So, it will actually be x dot del L del x dot plus y dot del L del y dot plus z dot del L del z dot. If you properly calculate this from this Lagrangian, this will be given by, okay, so m x dot square plus y dot square plus z dot square. Okay. And now, if you just say that my L is half m by 2 actually, x dot square plus y dot square plus z dot square minus v x y z, that minus, so then L minus this thing which I can now call minus h, I can say, so minus h will be equal to this whole thing minus this, so this will be minus m by 2 x dot square plus y dot square plus z dot square minus v, okay. And you can, I think, remember what this is. H is equal to, okay, m by 2 x dot square plus y dot square plus z dot square plus v. So, this function H is nothing but the total mechanical energy. This is the kinetic energy, this is the potential energy. You started with T minus V, you come with a form T plus V. So, you see this is also consistent with our conclusion that this is the motion of a particle which is moving in 3D space under a potential, because we know that potential means this is moving under a conservative force. So, the total mechanical energy should be conserved, okay, and this function, okay, is actually conserved. So, where this quantity which looked strange for us, now we know for a simple particle, okay, single particle moving in 3D space with some associated to some potential, this quantity is nothing but just the minus of its total mechanical energy, and since the total mechanical energy is conserved, this is also conserved. Okay. You can just try to find this function for other Lagrangians as well. Okay. Remember that this form T plus V is very specific to a mechanical system, okay, and it may not be the form of this function in general for other systems. Okay. Thank you very much.